Welcome to the second lecture on the computational complexity of algorithms. In this lecture, we're not really going to define any new concepts. Instead, we're going to perform time complexity analysis on algorithms, and these algorithms will be matrix algorithms. So in this first segment, let me start by defining some terminology pertaining to matrices. So a matrix is basically a two-dimensional array with rows and columns. In our case, we're only going to deal with matrices of integers. So the dimension of a matrix are defined by two numbers. The first number is the number of rows, and the second number is the number of columns, both of which are integers. So let's consider a particular case of matrices. Those are called square matrices because they have the same number of rows and columns. And let's call this number n. So an n by n matrix A is a two-dimensional table with n rows and n columns, like this one. Each element in the matrix is denoted by lowercase a and then two indices. For example, this element a sub 0, 0 is the element of the matrix uppercase A on row 0, column 0. So please remember that in computer science we start indexing at 0. So the first row is index 0, the next one is 1, all the way up to n minus 1 since the matrix has n rows. Similarly, the first column has index 0, the second one has index 1, and the last one has index n minus 1. You can ignore the coloring for now. So make sure you remember that the first index in an element is the row index, and the second one is the column index. That will always be the case. Notice this subscript notation, especially with long subscript with commas in them, is pretty hard to read. So in our pseudocode, to refer to the matrix elements, we're going to use the standard array indexing notation from most programming languages, namely the one with brackets here, instead of the subscript notation. So to refer to the matrix element on row R and column C, we're going to use this notation where uppercase A is the name of the matrix, the first number in brackets is the row index, and the second number in brackets is the column index. Now, again, matrices do not have to be square matrices. In general, the number of rows does not have to be equal to the number of columns. And in this lecture, we're only going to deal with square matrices. And the good thing is that square matrices have properties that are not shared by all matrices. For example, this concept, the concept of the diagonal, only applies to square matrices. So we define the main diagonal or the principal diagonal of a square matrix of dimension n by n as the sequence of elements aii, where the row index and the column index are equal, for I equals 0 up to n minus 1. So the elements on the diagonal are shown in red here in the figure. This is called the main or principal diagonal to distinguish it from other kinds of diagonals that are used in mathematics textbook. Now we're not going to talk about any other kinds of diagonal in this course, so we can just call it the diagonal. Notice the diagonal for us is always the sequence of elements from the top left corner to the bottom right corner. There's n such elements since the index goes from 0 to n minus 1. And notice a rectangular matrix where the number of rows and the number of columns are not the same does not have a diagonal because in a rectangular matrix there is no straight line or sequence of elements that go from the top left to the bottom right corner. In a rectangular matrix, there are either extra columns here on this side or there are extra rows down below. So there's no way to be at the diagonal. Now let's focus our attention on the blue elements in the figure here. What is the common property of all these elements? I'll give you a few seconds to think about it, and please stop the video and take your time. Well, visually, the blue elements are all above and to the right of the diagonal. Now, what is the property of the elements on a diagonal? They have the same row and column indices. So let's focus, say, on the elements on the first row. Notice all the blue elements on the first row have a column index greater than 0, which is the row index. The column index goes from 1 to n minus 1. On the second row now, all the blue elements have column indices from 2 to n minus 1. And again, all of these are larger than 1, which is the row index. So this is going to hold for every row, including the last one with a blue element in it. This is row n minus 2. The only blue element has column n minus 1, which is larger than the row index. So the common property of all the elements in blue is that their column index is strictly larger than their row index. Now, if you have a matrix where all of these blue elements are equal to 0, then this matrix is called a left triangular matrix or lower triangular matrix. The reason for this name is because if all the blue elements are 0, then the elements that matter in the matrix are all of these black and red ones, which form a triangle in the bottom left of the matrix. And therefore the matrix is triangular, and the triangle is either in the lower part of the matrix or to the left, depending on how you're looking at it. So, for a lower or left triangular matrix, all the elements a, I, j, when j is strictly greater than I, must be equal to 0. Of course, the red and black elements may or may not be equal to 0. That is not part of the definition. Our last definition has to do with a special case of these lower triangular matrices. What if not only all the blue elements here are 0, but so are the red elements? In that case, we still are left with a lower triangular matrix, here the black elements. But when the red elements are also all equal to 0, we have a special case of matrices called a strictly lower or left triangular matrix. So again, the definition for this kind of square matrices is that the elements a, I, j, where I is the row index and j is the column index as always, these elements are equal to 0 for every element such that j is greater than or equal to I. So the only difference between this definition and this one is that here we added an equal sign, and therefore we include the diagonal elements in the restriction that these elements must also be equal to 0 in addition to the blue one. So this is the only terminology you will need in this lecture to understand the algorithms that are coming up in the next segments. Make sure you're comfortable with this terminology. I will not come back to it when I describe the algorithms. The rest of the lecture will focus on studying the computational complexity and more specifically the time complexity of the algorithms that operates on these square matrices.